All right, kids, here we go. This is the review for mole and percent comp by mass. You need a calculator, you need a reference table, and you need the mole island maps. It's going to help. In the next 35 minutes, you're going to own this. You're going to figure it out. You're going to do it. You got to try. Please let me try to assure you how important this is. All right, it is hard, right? Especially if you've not been paying much attention and not been doing too much of the work. But this is only the beginning. Moles and percent composition will grow into something called stoichiometry. First, we're going to have to learn about chemical reactions. That's going to take several weeks to learn how to balance equations and see all the different kinds of chemical equations there are. Then we're going to combine moles with reactants with moles of products, grams and liters and particles and molecules and grams, all these different combinations. Moles is important. You can't just skate by this. This is important. This is basic chemistry. We've learned a lot of stuff to get to this point, but this is the first nugget of what you have to learn. So here we go. You have this gigantic number of 4 millunits of sodium chloride, and we have to convert it into grams. So let's look at the map. We're starting on particle island. We're starting with 4 millunits. Particles can be atoms or molecules, or in this case, 4 millunits. We're going to have to get to the other side, which is mass island. The only way to get from particles is to go to moles, and then moles comes down to grams. It's 2 steps. The first step is to put the starting point over 1, 4.87 times 10 to the 24th 4 millunits, and the conversion factor, or the toll on that bridge, 1 mole is equal to Avogadro's number. Since we have 4 millunits in the numerator to start, we put 1 mole over Avogadro's number of 4 millunits, and the 4 millunits cancel. Now, to do this math problem, we're going to have to combine this math, and we're going to get 4.87 divided by 6.02. That's the numerators, and then the numerator and denominator. That's the coefficients, and then we're going to have the exponents, numerator, denominator, divide. So this works out to 0.809 times 10 to the first. 10 to the first is another way to say 10. Let's get rid of this exponent. 0.809 times 10 is 8.09s of moles. Now, that's only the moles. All this math, all this writing, we're only halfway there. We went from 4 millunits to moles. This many 4 millunits is the same as saying 809 moles. Now we have to convert to grams. And to do that, we're going to need the molar mass of sodium chloride. And somewhere off to the side, you're going to have to write NaCl and then list underneath NaCl. 1 times 23 grams for sodium and 1 times 35 grams for chlorine. And that's 58 grams per mole. The moles in the numerator means in the conversion factor, we put moles in the denominator. And the answer pops out 469 grams of sodium chloride. This is just a little more than a pound, right? A pound of salt is 454. This is a little more than a pound, but it's a gigantic number of formula units. 2 steps. Use the map, watch your significant figures, and make sure all your units cancel out. Now, you have 125 grams of carbon dioxide gas in a balloon. And in our class, for now, all of our gases are at STP. STP means standard temperature, and it also means standard pressure. All that means for now is that exactly 1 mole fits in 22.4 liters. If pressure were higher, we'd squash the gas. If pressure were lower, it would expand. If the temperature was hot, the gas would expand. And if the temperature was cold, the gas would shrink. But at STP, at standard, we know that exactly 1 mole is exactly 22.4 liters. All of our gases are going to be at STP until later in the year. In this case, we're going to go from grams, or mass island, on the bottom, and we have to go all the way to the top to volume island in liters. This is 2 steps. We have to go from grams to moles, and then moles to liters. In the first step, we're going to convert. We're going to have what's called the molar mass of carbon dioxide. Off to the side, CO2, and you're going to list the atoms, CNO. 1 times 12 is 12. 2 times 16 is 32. And carbon dioxide is 44 grams per mole. Now, I didn't show all that because you're supposed to know this by now, right? This is the 4th or 5th class. We've been doing this, homework problems. You got to know you need the molar mass, and we know how to figure out the molar mass. You just have to remember to do it. 125 grams of carbon dioxide is 2.84 moles of carbon dioxide. Now we have to convert the moles of carbon dioxide into liters. And since it's at STP, we know that 1 mole equals 22.4 liters. So we're going to move the 2.84 moles over 1, and then we're going to use this conversion factor. We put moles in the denominator so the moles cancel, and 22.4 liters is on top, and with 3 significant figures, the answer pops out. This is the biggest kind of a mole problem, 2 steps. We start in one corner, we go to a different corner, right through moles. Everything goes through moles. Moles is central in chemistry. Now, 888 grams, that's just a silly number, of copper Roman numeral 2 sulfate. How many formula units, FUs? That's particles. Now remember, if you're an ionic compound, you exist in a crystal form. You do not exist as individual molecules like water or carbon dioxide. You exist in a crystal. So you have the idea of a single COSO4, but you don't actually exist as that. You exist as billions and billions of them at the same time in a single crystal. So we're going to go from mass to moles, and then we're going to go from moles to particles. So in the first step, somewhere in your head, you got to have the molar mass. And we just did this in the notes a couple of pages back. COSO4 is one copper, 1 sulfur, and 4 oxygens. It's 160 grams per mole. So if you have 888 grams in the numerator, you got to put the grams in the denominator for the conversion factor. This is going to equal, how cool is that? 888 becomes 5.55 moles of copper Roman numeral 2 sulfate. That's the first step. We want to know how many particles. So we're going to move the 5.55 moles over 1, and we're going to convert it because we know that there's Avogadro's number of formula units in a mole. So in this big math problem, it's going to be 5.55 times 6.02. We'll put that in parentheses. We're going to do that part first, times 10 to the 23rd. So this is going to equal 33.4 times 10 to the 23rd, but 33.4 is no good. We have to make it less than 10, so we make it 3.34. We make it 10 times smaller. We have to make the exponent 10 times bigger to keep it even. 3.34 times 10 to the 24th formula units. 58, 67.2 grams of water. I'm going to drink that much right now. It's not that much. 18 grams is a mole. Now, in this question, it says you have 67.2 grams of water. How many grams of just hydrogen? That big sip. I drank water made of hydrogen and oxygen. And it says round to the nearest whole number. Okay, so to do this, we need the molar mass of water, which of course is 18 grams per mole, right? 2 times 1 and 1 times 16, 18 grams per mole. Now on the right side, now we're going to do the percent composition by mass. This is in the notes. You might even have it in your head. And hydrogen makes up 11%, right? Because it's 2 grams out of the 18 grams times 100%. And the oxygen is 16 grams out of 18 grams times 100%. And we should add that up, right? 11 and 89, that's 100%. Yeah, we did it right, 100%. Water is 100% hydrogen and oxygen. 11% hydrogen by mass and 89% oxygen by mass. Now the question is, out of those 67.2 grams I just drank, how many grams are just hydrogen? We have to change 11% into a decimal. We're going to multiply how much we started with times 0.11. And that is going to be 67.2 times 0.11 is going to equal 7.39 grams of just hydrogen. Now I think, let me roll back here on the notes. I think this round whole number percent, so we went to 11% instead of 11.1111 and 88.9999. So it's 11% and it's 7.39. If you misread that, it would be 7 grams of hydrogen, but technically 7.39 is the correct answer. In this question, percent composition by mass of nickel in nickel Roman numeral 2 carbonate. Now, if you put your finger in the nickel box, nickel makes a +2 ion and a +3. We're going to use the +2 one. Carbonate is on table E. Carbonate's a -2 ion. So on the left side of your page, you're going to do the molar mass of NiCO3. 1 nickel, 1 carbon, 3 oxygens. 1 times 59, 1 times 12, and 3 times 16, 119 grams per mole. Now, on the right side, we're going to do the percent composition by mass. This is not hard. What is it asking you? You got to pay attention. What is the question? Because you know how to do all these steps. So we're going to do the percent composition by mass on the right. Now, I circled the top one because that's the only one that's the question, but we want to make sure we do the nickel percent comp, the carbon percent comp, and the oxygen percent comp so that we make sure we get 100%. Because you might just type in the wrong number by mistake in the calculator and just get an answer with the equal sign. Say, oh, there it is. Not if it's a mistake. So you do all 3 parts, but the answer, 49.6, or you could round it to 50%, right? That would be okay too. But the answer is in the red circle, but we do the carbon and the oxygen percent comp to make sure we get to 100%, to make sure we don't make a dopey mistake. Now, empirical formulas, we talked about these, right? They're stupid. Empirical formulas are the mathematically reduced ratio of atoms to atoms to atoms, but it's written like a formula just to screw you up. Paraffin wax is a type of wax. Wax is just giant hydrocarbons, right? Methane is CH4, that's the smallest one. This is 26 carbons and 52 hydrogens. They're both even numbers. You can divide them both by 2, right? And then we're going to get, oh, I guess they're all going to pop out at once this time. So let's just see what we got. The first one, 26 to 52, is a 1-to-2 ratio. So we get the same empirical formula, CH2. For ethene, C2H4 is that compound. 2 to 4 is also 1-to-2. Decene, C10H20, that's also CH2. Those 3, the first 3, all have the same empirical formula. 3 totally different compounds, different formulas, different properties, different names, different everything. Same empirical formula. What does that mean? Don't mean too much to me. It means they have the same 1-to-2 ratio of carbons to hydrogens, but they're not the same. Sucrose, C12H22O11. That's a really big molecule, but we have even in odd numbers, and we can't reduce that at all. So the formula for sucrose is also its empirical formula, making it a maximally stupid problem to do, but shows up on the regions. Heptane, C7H16, again, odd number, even number, no way to reduce that. So the molecular formula is the empirical formula as well. HCl, 1-to-1, can't be reduced. Potassium sulfite's an ionic compound. It's in a 2-to-1-to-3, and that can't be reduced anymore. And the last one also, cobalt Roman numeral 2 phosphate, can't be reduced anymore. Now, how many electrons are in these particular ions? The magnesium positive 2 ion. Now, magnesium has 12 electrons. 12 electrons, but this is a positive 2 ion. So that means you lose 2 electrons. So the magnesium cation only has 10 electrons. 10. Can I see that? 10. Now, aluminum. Aluminum is a 2-8-3. Aluminum has 13 electrons, but if it's a positive 3, what does it get? It gets 13 electrons. The positive 3 is just 10. I guess they're going to come up in pairs. Let's do these quickly. Cobalt has its element number 27. So cobalt positive 2 loses 2 electrons. Cobalt positive 3 loses 3 electrons. So the species called cobalt Roman numeral 2 has 25. That's 27 minus the 2. The species called cobalt Roman numeral 3 has 27 minus 3, or 24 electrons. Now, Pb is lead. There's 2 species of lead ion, Pb positive 2, Pb positive 4. Lead is element number 82. So if you have 82 and you lose 2 electrons, that gives you 80 electrons. If you've got 82 electrons and you lose 4, that gives you 78 electrons. And somehow or another, these elements, they bend and switch and futz around. They become stable with different numbers of electrons. Fluorine has 9 electrons, 2-9. Negative 1 ion means it's gained an electron. That makes it 10 electrons, makes it isoelectric to an open gas. Sulfur is 2-8-6, 16 electrons. But if it gains 2 electrons, it's going to have 2 more than normal. So the sulfur atom has 16 electrons, but the sulfur -2 anion has 2 extra. Nitrogen is element 7. It's got 7 electrons, 2-5, but when it becomes a -3 ion, it gains 3 electrons. It's going to end up with 10 electrons. Gold is atom number 79. That means it's got 79 electrons. If it loses 1 electron, 79 minus 1 is 78. Now, gold with 79 electrons might lose 3 electrons. And what happens to that then? It becomes 76 electrons. Copper, with no symbol, that's an atom. Copper is element 29. That means it's got 29 electrons right on the periodic table. Chlorine has 17 electrons, 287. But when it gains 1 electron to become isoelectric to a noble gas, it becomes 18. Iron is element 26. That has 26 electrons. There's no charge there. Sodium has 11 electrons, but if it becomes a positive one ion, it loses 1, becomes isoelectric to neon, 10 electrons. And the species called Mn+7. Mn is element 25. If it loses 7 electrons, it's down to 18 electrons. Species is a funny word, usually refers to biology, right? What species is this? A different species than that. For instance, in the top row there's 2 cobalts. There's cobalt atoms, cobalt +3 or cobalt +2. There's 3 species of cobalt. Aluminum comes in atoms or +3 ions. 2 species of aluminum. Lead comes in +2, +4, and neutral atoms. 3 species. All that word means is types in this case. We don't really have species. Elements are not somehow biologically differentiated from each other. They're not biological. This is chemistry, not biology. All right. If I were you, I would do these questions in review again, right? Do the math again. Go back to the beginning, do the math, and then use the Zoom or the answers to see if you get them correct. Studying means you have to do work. You don't want to just look at stuff. You got to get some blank paper. You have to write stuff out, and you have to make sure you know how to do this. Chemistry is golden. That means number 79. Chemistry is good, and that's important. And not everybody's getting it yet, but everybody should, which means you got to practice. Okay, we're going to do some more, one more lab, and then we're going to just keep practicing. Hopefully you're going to do swell on this. All right, thanks for playing. Bye.